The wreckage lay sprawled across the valley like the skeleton of some mechanical leviathan. Aluminum ribs jutted from the earth, twisted and half-melted, their edges blackened by the blast. The air smelled of scorched oil, cordite, and burnt insulation, the residue of an air war that had finally come to Japan's own soil. A handful of civilians, farmers mostly, stared from the ridgelines, whispering the same phrase under their breath. Boeing. America no Bakudan ki. Under armed escort, teams from the Imperial Japanese Army's Air Technical Research Institute descended upon the site before sunrise. The charred tail section still bore faint traces of block lettering B-29 Superfortress, though the American insignia had been burned away. What remained of the fuselage gleamed in the morning mist like the flank of a whale. Among the scattered debris, engineers found something they had never seen before: hermetically sealed fuselage sections, double-skinned and lined with rubber gaskets, portholes with glass that refused to shatter even when struck with hammers. Lieutenant Colonel Masaru Okabe, the senior engineer on site, crouched near one of the intact sections. "This aircraft," he said quietly, "flew higher than anything we possess, higher than the Zero, higher than even the Ki-46. He placed his hand on the curved wall of the fuselage. And yet, the crew sat in comfort, heated, pressurized. They breathed like on the ground. A second officer, younger, skeptical, muttered, "Impossible." "Not at 10,000 meters." Okabe shook his head. "Not impossible, Lieutenant. American." 2 days later, crates began leaving Yawata under armed convoy. The engineers carefully detached the forward pressure bulkhead, portions of the cockpit canopy, and segments of ducting that still held remnants of wiring and valves. The order came directly from Tokyo. Preserve all environmental and oxygenation equipment. Send to Germany via I-29. That submarine, the I-29, one of Japan's secret exchange vessels, waited in Singapore. By July 10, the metal crates marked Special Research Material, Luftwaffe Liaison, were sealed and loaded aboard. Inside them lay the heart of the B-29's mystery, fragments of the world's first fully pressurized combat aircraft. The boxes arrived weeks later, their contents escorted under Gestapo supervision to the Luftwaffe's secret testing center. The man summoned to receive them was Dr. Rudolf Mayer, chief of the pressurization development team at the Deutsche Luftfahrtforschungsanstalt, DLH Technisches Amt. Mayer, a tall, severe figure in his late 30s, had spent years working on altitude systems for the Heinkel He 177 and the abortive Ju 388J project. His office, lined with blueprints and failed prototypes, reeked of stale coffee and graphite. When the first crate was opened, Mayer froze. Before him lay the curved skin of an aircraft unlike any he had touched. The aluminum alloy was smooth and faultlessly joined, no rivet heads visible, only seamless flush riveting, polished like mirror glass. He traced his finger along the edge of a circular window and frowned at the laminated structure of its glass. "Triple pane," he whispered. And, sealed under pressure, his assistant, Oberingenieur Franz Dietrich, peered over his shoulder. "Is it from the Americans?" Mayer nodded. "Yes. Boeing. A Superfortress, they call it. They've built an aircraft that flies higher than our interceptors, and their men inside sit as though in a parlor." They laid out the contents: ducting lined with insulation, fragments of pressure bulkheads, a partially intact regulator marked with English text, "Cabin Pressure Control, Valve Boeing Aircraft Company, Seattle, Wash." Mayer turned the valve in his hands and exhaled slowly. "This is not a simple oxygen system. It is an atmosphere. They have created an artificial Earth inside their machine." For weeks, the German engineers studied the components under magnification. They dissected each fitting, each valve, and compared them to their own Me 264 and Ju 388 pressure cabin experiments. The contrast was humiliating. Where the Germans used crude rubber seals that leaked under stress, Boeing's used synthetic compounds, neoprene and silicone, that flexed yet held airtight. Where German valves jammed above 6 kilometers, the American regulators functioned smoothly to 10, and where German compressor turbines failed after 20 hours, the U.S. system was modular, field replaceable, and designed for hundreds of flight hours. Late one evening, Mayer dictated a report into his recorder. Preliminary analysis indicates a level of metallurgical control beyond current German capability. The alloy composition, probably a high magnesium duralumin, maintains tensile strength even at 50 degrees Celsius. The system's layout is not experimental, but industrial evidence of serial production. The Americans have not only achieved pressurization, they have standardized it. He paused, adjusting his spectacles. We can imitate the design, but not its materials, and imitation without material equivalence is folly. By early September, the Luftwaffe ordered Mayer's team to create a German version for the projected Heinkel He 274, the high-altitude bomber meant to rival the B-29. The Reich Air Ministry expected results within 6 weeks. Mayer wrote privately in his diary, "Berlin demands that I make mountains breathe like valleys, but our metals corrode, our seals fail, and our turbines freeze. They think physics obeys politics." He was not wrong. The alloy samples they received from Reichswerke Hermann Göring oxidized under laboratory pressure cycles. The synthetic rubbers from I.G. Farben decomposed at altitude temperatures. Each test ended the same: leaks, fractures, failures. And yet, somewhere above the clouds, real B-29 already flew from bases in China, their pressurized cabins carrying men named Reynolds, MacDonald, or Kemp to altitudes where even the Luftwaffe's best fighters could not reach them. Mayer looked once more at the curved fuselage section under the Rechlin lamps. He could see the rivet lines reflect like veins. He murmured to no one in particular, "They've made the air itself their armor." Outside, night descended over the airfield. A Ju-188 roared into the dark, unpressurized, trembling, its crew wrapped in layers of fur and desperation. Inside, Dr. Rudolf Mayer sat alone beside the American metal, listening to the distant engines fade. For the first time, the proud engineer of the Reich understood what defeat would sound like. A low hum, high above reach, wrapped in airtight silence. The laboratory was lit by the cold glow of mercury lamps. On the central table, a section of the B-29's fuselage gleamed beneath a fine mist of frost. Condensation from the night's humidity gathered and froze on its surface, an accidental recreation of the stratosphere in miniature. Around it stood 5 engineers, men whose faces had grown pale from sleepless nights and cigarette smoke. Dr. Rudolf Mayer paced slowly around the artifact. In his notebook were figures that refused to reconcile with any known Luftwaffe design. The pressure differential alone, 8.6 pounds per square inch, meant that the structure carried the stress equivalent of an artillery shell casing at cruising altitude. Yet the American aluminum skin measured only 1.4 millimeters thick. He turned toward the group. "How does it not tear itself apart?" he demanded. Dietrich, his assistant, shrugged helplessly. "Their alloy. It's too refined. The molecular grain is tighter. When we run tensile tests, ours fracture at half the load." A junior metallurgist, Weiss, added nervously, "We have samples from duralumin 24ST and the new electron-magnesium blend, but neither performs. The Americans are using something else, perhaps heat-treated to a pattern we cannot duplicate." Mayer leaned over the sample and traced his finger along the seamless rivet line. "They build not with metal, but with mathematics. Every joint calculated to equalize stress. This is not craft, it's science." Outside the hangar, the late summer air vibrated with the drone of distant engines. Rechlin's test flights continued despite the growing raids across Germany. The engineers often paused mid-discussion as Allied reconnaissance planes circled overhead. Each time, the sirens wailed, and they would drag tarps over the crates from Japan. Inside, Mayer's mind drifted back to the reports from Yawata. Japanese technicians had described the B-29's interior, a tunnel linking the forward and aft compartments through a pressurized tube, crewmen working in shirt sleeves while flying at 9,000 meters. Heated cockpits, oxygen control systems, and electric de-icers on the propellers. To men who still flew at -40 degrees in unpressurized Heinkels, it sounded like myth. He opened a folder stamped Luftwaffenführungsstab, Geheim, and began reading aloud from the intercepted American technical bulletins the Abwehr had stolen months earlier. B-29 crew environmental system automatically maintains cabin altitude at 8,000 feet to an aircraft altitude of 32,000 feet through use of a pressure regulator and manifold relief valves. Uses cabin superchargers to pressurize air conditioned by evaporative coolers. He stopped. Air-conditioned, he repeated softly, almost in disbelief. Dietrich smirked bitterly. Meanwhile, our He-177 crews suffocate on carbon monoxide. The room fell silent. Mayer decided to conduct his own test. On August 15th, the engineers mounted a reconstructed cabin section in Rechlin's altitude chamber. They patched every joint they could, using German rubber seals and bolts. When the pumps started, the chamber hissed and creaked like a dying beast. "Pressure holding at 3,000 meters equivalent," the operator called out. "Take it higher," Mayer ordered. At 6,000 meters the gauges began to flutter. The joints trembled, bolts strained, and a sharp pop echoed. One of the seals tore open, venting a white plume of vapor. The test ended there, the cabin pressure collapsing with a hiss. Mayer removed his headset and stared at the frosted window. "We cannot cheat physics," he said quietly. "The Americans don't simply trap air. They manage it. Every molecule moves according to a design." He spent the following nights drafting new schematics, a double-layered hull, automatic valves synchronized to engine output, and pre-stressed bulkheads to distribute differential load. But each drawing carried red annotations. Requires new alloy, unobtainable pressure pump, synthetic rubber deficit. At the same time, another document arrived from Berlin. A directive from the Reichsluftfahrtministerium, RLM, accelerate studies on American pressurization technology for application to Heinkel, He-274, and Ju-388J. A working prototype expected by November. Present results to Field Marshal Milch personally. Mayer felt the paper grow damp in his hands. November less than 3 months. He knew it was impossible. The factories in Dessau and Augsburg already lay in ruins. Rubber supplies were gone, compressor units scarce. Even the electrical relays they needed now came from scavenged civilian radios. He dictated a message to his assistant for transmittal through the chain of command. "The primary obstacle is not theory, but materials. German science can replicate the design in principle, but metallurgy and chemical industries cannot sustain the tolerances required. Until the Reich controls its environment, its heat, its pressure, its resources, it cannot control the air." The reply came 2 days later, signed by an RLM adjutant. "Proceed regardless. Victory demands innovation." By September, Mayer's frustration turned philosophical. He began writing long notes in his personal journal reflections, less of an engineer than of a man confronting the limits of his civilization. "The Americans have conquered altitude because they believe it is conquerable. We, bound by shortage and ideology, demand miracles without the patience for molecules. Our physics are sound, but our politics are diseased. We fight the stratosphere with slogans." He attended a briefing at Rechlin's main hall, where Luftwaffe officers displayed blueprints of the Me-264 America bomber. A colonel lectured about reaching New York City by air. Mayer sat quietly, knowing that at 30,000 feet their unpressurized cabins would freeze their crews solid long before the Atlantic was crossed. When the meeting ended, he walked outside. The autumn air carried the scent of burning fuel. Rechlin's night test flights had begun again. From the runway, he saw the silhouette of a Ju-388 lifting off, its nose gleaming in the moonlight. For a moment, he imagined what it would feel like to sit inside a true pressurized aircraft: warmth, steady breathing, silence, the opposite of everything around him. He returned to his lab, switched on the lamp, and stared at the American valve one more time. Stamped into its base, faint but still legible, were the words, Boeing Aircraft CO, Seattle, Washington. He traced the letters with his thumb, whispering almost reverently, "They understand that mastery of air begins with mastery of comfort, and comfort, for us, has become treason." Outside, the sirens began again another Allied raid somewhere to the west. The engineers extinguished their lights. In the darkness, the fragment of the B-29 glowed faintly from the reflection of distant fires, a relic of an industrial civilization that had already leapt a decade ahead. While the Reich still fought with steel and fear, Mayer closed his notebook and listened. As the bombers passed overhead, invisible, untouchable, encased in air their machines alone could breathe. The first chill of autumn crept into the test hangars. Dew gathered on the broken skylights, dripping onto drafting tables littered with blueprints and cigarette ash. Dr. Rudolf Mayer arrived before dawn, as he always did, his overcoat already powdered with frost. Inside the experimental bay, the skeletal frame of a half-finished cockpit gleamed under the weak lamps the Heinkel pressurization test rig, a desperate attempt to graft American engineering onto German airframes. Around him, engineers worked in heavy silence. Every few minutes, someone coughed or stamped their boots to keep warm. The war had stripped Rechlin bare. They scavenged components from wrecked aircraft, repurposed oxygen tanks from hospitals, and used salvaged copper wiring from abandoned factories. Mayer placed his notebook on the table. "Gentlemen," he began quietly, "today we begin pressurization trials on the Heinkel system, version 3. Dietrich, his assistant, looked skeptical. "The seals will fail again. The Heinkel compressor isn't stable beyond 6,000 meters. "I know," Mayer said. "But the ministry wants data, not excuses." He turned toward the prototype, a crude cylinder of aluminum segments, bolted and patched, wired to gauges. It resembled a pressure chamber built from scrap, which in truth it was. The men donned their earphones as Mayer signaled to start the pumps. At first, the hiss was steady, a low rumble as the cabin began to pressurize. The dials climbed slowly, 2,000 meters, 3,000, 4,000. Mayer's hand hovered above the emergency cutoff. 5,000 meters, the operator called. Mayer nodded. "Hold it there." The walls creaked ominously. One of the rubber seals bulged, then held. For a few seconds, the system stabilized. A faint smile flickered across Mayer's face. "We're close," he whispered. Then came the crack. A joint split open with a metallic shriek. Air burst through in a freezing jet, scattering papers and dust. The lights flickered and went dark. The chamber's inner skin peeled apart like tinfoil. When the noise subsided, the test bay was silent except for the hiss of escaping pressure. Dietrich tore off his headset. "Failure again." Mayer didn't answer. He stared at the ruined section, the aluminum warped, the seal shredded. He ran his hand over the fracture and said quietly, "This is what happens when you ask a candle to burn like the sun." That evening, Mayer wrote a detailed failure report for the RLM. His handwriting was cramped, the ink smudged by fatigue. "At current industrial capability, construction of a stable pressure vessel is beyond our reach. The combination of thin-gauge duralumin and existing rivet tolerances cannot sustain the required pressure differential without catastrophic deformation. Suggest suspension of program pending material breakthrough." He did not expect it to be approved. The Reich never suspended anything anymore. Sure enough, the response came 2 days later from Berlin. "Continue testing. Results will be presented at the Führerhauptquartier before month's end." The implication was clear: failure was no longer an option, only treason. Rechlin hosted an inspection team from the Technisches Amt, led by General Engineer Ernst Heinkel himself. The man's once proud stride was gone. He moved like a ghost of the early Luftwaffe glory days. His hair had turned white, his voice low and strained. Mayer guided him past the wrecked prototypes, explaining the B-29's system, the automatic valves, the thermostatic regulators, the flexible gaskets. Heinkel listened in silence, running his hand over the American alloy. At Dessau, We tried building a similar chamber for the He-274, Heinkel said. The material buckled under its own load. Yes, Mayer replied. They build with heat-treated, alloys alclad. Their entire system depends on mass production at atomic precision. We are building sculpture, not science. Heinkel gave a bitter laugh. I told Goering that long ago. He wants an altitude bomber that can reach America, but we can't even keep our men breathing over the Alps. The two men stood together by the wrecked cabin. Around them, the airfield echoed with distant artillery from the Eastern Front. Heinkel said quietly, You've seen their machines, Doctor. Tell me truthfully, could we ever match them? Mayer hesitated, then answered with the precision of an engineer. In spirit, yes. In reality, not within a decade. They have what we no longer possess: time, aluminum, and freedom to fail. Heinkel said nothing more. He simply nodded, touched the smooth American metal once more, and left the hangar without another word. In the following weeks, Mayer grew obsessed with understanding not just the machinery but the philosophy behind it. He studied captured Boeing manuals, handwritten notes from American technicians, and even fragments of English-language advertisements smuggled through Sweden. One phrase in particular haunted him: precision through repetition. He began to realize that Boeing's advantage wasn't secret physics or hidden genius, it was consistency. The Americans built thousands of identical parts under identical conditions, while Germany built a handful of prototypes under bombardment. Where Boeing employed disciplined standardization, the Reich relied on heroic improvisation. He wrote another note in his private journal. Our engineers are craftsmen. Theirs are systems thinkers. That is the true gulf between us, not intelligence, but infrastructure. By late October, the Allies were bombing German cities nightly. Rechlin's power supply faltered constantly. The pressure lab lost heat, and frost formed inside the test chambers. Engineers worked by lantern light, their breath visible in the cold air. One night, as Mayer reviewed test results, a young technician approached him, holding a crumpled telegram. Herr Doctor, he said hesitantly. The I-29, the submarine that brought the B-29 parts from Japan. It's been sunk. American destroyers. Mayer closed his eyes. Then what we have here, he said softly, is the last piece of that world. He stood and placed his hand on the surviving fuselage section, now dull with frost. Around him, the hangar was silent except for the wind whistling through broken glass. He knew the end was near not just for the project, but for the Reich itself. Still, he dictated one final message for his technical file. Recommendation. Future air power will belong to nations that can control the human environment as effectively as the mechanical one. The true frontier is not altitude, it is comfort, endurance, and the mastery of atmosphere. On the final night of October, the power failed completely. The hangar went black. Mayer stood alone in the dark beside the silent test rig. Somewhere above the clouds, unseen and unreachable, American B-29 seconds were already crossing into German airspace from Italian bases. Their crews sat in warmth and pressure, speaking of home. Mayer lit a cigarette, its ember glowing red in the darkness. He watched the smoke curl upward thin, steady, unbroken. For a moment, he imagined that inside those distant aircraft, the air itself obeyed man's command. He exhaled slowly and murmured to himself, They breathe victory. We. Only the past. Frost coated the runway like powdered glass. The trees beyond the perimeter fence stood bare, their branches skeletal against the grey dawn. Inside Hangar 7, a single bulb burned over the test stand, the last functioning light in the entire facility. Beneath it, the prototype Heinkel pressurization cabin, Series 4, rested on its wooden support frame, patched with scavenged sheet metal and wrapped in cloth to keep the cold from cracking the seals. Dr. Rudolf Mayer stood with a mug of black coffee, watching his technicians assemble the final fittings. His eyes were ringed with exhaustion. It had been 3 months since the first fragments of the B-29 arrived, and every day since had been spent chasing an atmosphere that refused to obey them. Compressor ready, Dietrich reported, his breath visible in the chill. We've reinforced the joints with steel collars. It might hold to 8,000 meters. Mayer nodded without enthusiasm. Then let's see if the air will stay where it belongs. He signed the logbook, test run 14. He 274 pressurization simulation. The pumps started with a groan. Pressure built slowly. The dials trembled. The hum deepened. 3,000 meters. 4,000. 5,000. The structure quivered but held. Mayer leaned closer to the gauge. Increase flow. At 6,500 meters equivalent altitude, the seals began to moan a faint, almost human whine as stress rippled through the rivet lines. The technicians watched in silence, ready to cut power at any sign of rupture. 7,000, Dietrich said, voice tight. Maintain. The hum deepened into a low vibration that ran through the concrete floor. Steam hissed from one valve. The aluminum skin bulged slightly, then stabilized. 8,000 meters, the operator called out. For the first time, the German system held steady. No leaks, no ruptures. The cabin remained intact. The engineers exchanged glances, unsure whether to cheer or hold their breath. Mayer finally exhaled. Record the reading. But the victory lasted only moments. A sharp metallic ping cracked through the room, followed by a deep groan as one of the steel collars buckled. The pressure gauge flicked red. Release valve, now! The emergency vent roared open, dumping the air with a violent hiss. The cloth wrapping the chamber whipped loose like a torn sail. When the noise subsided, the chamber sagged inward, one side, caved and fractured. Mayer removed his spectacles, wiping the frost from the lenses. That's it, he said softly. She's finished. 2 days later, a courier arrived from Berlin with an envelope marked Sofort, persönlich. Inside was a letter from the Technisches Amt requesting that Mayer prepare a demonstration for high-ranking visitors, including Field Marshal Erhard Milch and representatives from Heinkel and Junkers. Mayer stared at the order in disbelief. A demonstration? Of what? Failure? They want results, Dietrich muttered, even if they have to invent them. Mayer set the paper aside. Then we'll show them truth. No more illusions. The visiting delegation arrived under grey skies and the distant thunder of artillery. Milch, gaunt and trembling, inspected the wrecked pressure hulls with an expression somewhere between curiosity and despair. Beside him, Heinkel remained silent, his gloved hands clasped behind his back. Mayer began his presentation without notes. He spoke in clipped, factual tones, each word measured like a laboratory report. Gentlemen, this system represents our latest attempt to replicate the Boeing pressurization apparatus recovered from Japan. We achieved partial success at 8,000-meter equivalent altitude for approximately 2 minutes before structural deformation occurred. The limiting factors are alloy strength and seal integrity. Our chemical industry cannot yet produce synthetic compounds comparable to American neoprene. Metallurgical substitutes oxidize under stress. Milch frowned. Can you not reinforce the structure? Mayer shook his head. Reinforcement adds weight. The airframe collapses under its own load before it even leaves the ground. Pressurization is not simply an engineering problem, it is a materials revolution. The officers shifted uncomfortably. Heinkel spoke at last. You mean to say the Americans possess metals that we cannot make? Yes, Mayer replied, simply. They mass-produce miracles. For a long moment, no one spoke. Then, Milch gestured toward the wrecked chamber. Destroy it. The Führer will not hear of American superiority. We will tell Berlin the project proceeds. Mayer's expression did not change. It proceeds only toward gravity. The room fell silent again. Heinkel gave Mayer a brief, almost apologetic look before the delegation left. That night, Mayer remained alone in the hangar. Outside, bombers rumbled somewhere far above the same distant hum that had haunted him since summer. He climbed onto the ruined test rig, sat among the warped panels, and traced his fingers along the lines of torn aluminum. He thought of the men inside the B-29 sitting in heated, pressurized cabins, breathing easily as they crossed oceans and continents. He wondered if they knew what it meant that inside their aircraft, the very laws of nature had been bent into obedience. He opened his diary and wrote by lantern light. "I once believed war was a contest of courage. It is not. It is a contest of comfort, who can build the sky into a home first. The Americans have done so. We, trapped by ideology and scarcity, are still trying to build warmth from steel." He paused, listening to the engines fading northward. "They breathe civilization," he murmured. "We breathe fumes." A week later, orders arrived to relocate the research to Bavaria, as Rechlin prepared for possible evacuation. Mayer supervised the packing himself. Most of the prototype was scrapped for transport weight. Only one artifact was preserved, the original American pressure valve from the B-29, still gleaming despite months of use. When Dietrich asked why he insisted on saving it, Mayer replied, "Because someday, someone will need to remember what progress looks like." They sealed it in a wooden crate labeled simply, "Technisches Material. Unersetzlich." The snow fell heavily that morning. The airfield was silent, except for the distant rumble of trucks. As Mayer prepared to leave, he walked one final time through the abandoned hangar. The cold air stung his lungs. He stopped beside the dismantled compressor assembly and laid his hand on the frosted metal. He thought of the first day he'd touched the Boeing fuselage, the shock of its perfection, the quiet humiliation of realizing the Reich's scientific ceiling. He knew that what they'd failed to replicate was not merely a machine, but a mindset, a world where engineers built without fear. He turned off the lights, one by one, until the hangar was dark. Outside, snow swallowed the runway. In the distance, another formation of bombers droned overhead, invisible, steady, breathing air that Germany could no longer command. Mayer whispered, almost reverently, "They have learned to hold the sky in their hands. We never learned to let go of the ground." He stepped outside, closed the door behind him, and disappeared into the falling snow. The Bavarian Alps rose like jagged teeth through the fog, their peaks dusted with early snow. The Luftwaffe's new research facility had been hastily constructed in an abandoned aircraft hangar near Oberpfaffenhofen, chosen for its remoteness and concealment from Allied reconnaissance. The drive from Rechlin had taken 3 days, winding through bombed-out towns and frostbitten forests, the convoy of trucks laden with fragile prototypes moving under constant threat of air attack. Dr. Rudolf Mayer walked alongside the convoy, his coat collar pulled high against the biting wind. The air smelled of pine and coal smoke, a strange comfort after months of Rechlin's antiseptic hangars. He glanced at the crates containing the remaining B-29 fuselage segments and the single American pressure valve, the only artifact of a project that had nearly destroyed his team's morale. Inside the hangar, the work resumed immediately. Engineers unwrapped frost-covered panels and examined fractured seals. Mayer oversaw every step, his hands steady but his mind already racing ahead. He knew that even here, isolated in the mountains, the laws of metallurgy and physics would not bend to their ambitions. "This place is smaller," Dietrich remarked, his voice echoing off the bare walls. "We'll have to reduce the test runs. Only simulations for now." "Yes," Mayer replied, inspecting a cracked aluminum skin. "Our enemies do not need to know our failure. But we must understand it ourselves." By mid-December, winter had fully settled. Snow pressed against the hangar doors, and the days were short, the nights long and bitter. Mayer worked under dim electric lights, poring over schematics, cross-referencing the original Boeing blueprints against the fragmented materials. Each calculation, each adjustment, revealed the same truth. Germany's metallurgical capacity could never replicate the alloys that allowed the B-29 to sustain pressurized flight at 9,000 meters. Yet, despite the limitations, Mayer insisted on continued experimentation. Small-scale models, test chambers, and improvised seals became the lifeblood of the team. The American ingenuity embedded in each rivet and panel became both a standard and a spectre. One evening, Mayer walked to the edge of the facility, looking out over the fog-shrouded mountains. The horizon was a vanishing line of grey and white, endless and unyielding. He felt the weight of the Reich pressing against him, the demands of impossible expectations, and the quiet, undeniable lesson from the distant B-29 seconds. Mastery of the sky required more than engineering skill. It required resources, foresight, and freedom from fear. He returned to the hangar, the snow crunching beneath his boots, resolved that the work would continue, not as a path to victory, but as a record, a measure of how far they had reached and how far they had fallen short. The first full month of 1945 pressed down on Germany like the snow, outside the hangar relentless, cold, and unforgiving. Inside, the Luftwaffe engineers labored under the harsh glow of incandescent bulbs, their breath clouding the air in shallow plumes as they examined the pieces of the B-29 fuselage. Every panel, every rivet, every valve was a puzzle they were compelled to solve, but the laws of physics and material science were an unyielding adversary. Dr. Rudolf Mayer stood at the center of the hangar, staring at a cross-section of a pressurized cabin segment suspended on a makeshift rack. The aluminum alloy was flawless by American standards, thin yet capable of holding near-constant pressure at altitudes beyond 30,000 feet. Mayer traced a finger along the seam, where two panels met. His mind ran calculations, comparing the material properties to the best German aluminum available from Reichswerke and IG Farben factories. Every calculation ended the same way. German metallurgy lacked the tensile strength and ductility necessary for sustained pressurized flight at those altitudes. Dietrich, his assistant, approached with a small clipboard. "The chamber tests again failed," he said, exhaling a cloud of vapor. "We achieved only half the necessary pressure before the seams buckled. Even with reinforcement, the material fails before sustaining full operational altitude." Mayer rubbed his temples. He had anticipated the limitation. But the failure carried more weight than he expected. It was a tangible reminder that their efforts, however brilliant, were bounded by industrial realities. The Americans, meanwhile, had solved these problems with industrial capacity, precision manufacturing, and unrelenting access to resources, a combination Germany could no longer match. He moved to a bench scattered with small valves and gauges, salvaged from the B-29 segments. These components, though diminutive, were the linchpins of pressurization. The American design used a dual redundant system, ensuring stable cabin pressure even during engine failure or sudden altitude changes. Mayer had attempted to replicate it with German equivalents, but differences in material tolerances, spring constants, and valve clearances caused repeated failures. Each test ended in hissed leaks or ruptured test chambers. "We can copy the design," Mayer said quietly to Dietrich, "but we cannot replicate the materials. Without them, the system is doomed." The statement was not pessimism, it was fact. The limitations of physics were absolute. No amount of ingenuity, welding, or makeshift alloys could substitute for the unique combination of aluminum alloys, sealants, and precision engineering that Boeing had developed. Germany's engineers were talented, but the Reich's strategic situation, its bombed factories, and its stretched supply chains had rendered perfection impossible. By mid-January, Mayer had shifted focus from creating a functional pressurized cabin to studying the failure modes themselves. Every test, every rupture, every cracked seal became data. He documented meticulously, aware that even if Germany could not fly a B-29 copy, understanding why it failed might inform future high-altitude designs. The engineers constructed scaled-down models of fuselage sections, subjecting them to incremental pressure tests inside small chambers. They watched rivets shear, panels warp, and seals rupture. Mayer recorded each observation: the thickness of aluminum versus pressure thresholds, the deformation of seals under temperature variations, the stresses on rivet lines. Slowly, patterns emerged. They could see exactly where the German material was failing, exactly how the American design compensated, and exactly why their own attempts were insufficient. Even in the bleak midwinter, morale flickered in small victories. When a test chamber survived pressure for a few seconds longer than expected, the engineers celebrated quietly. It was not triumph, it was proof that understanding was possible, even if replication was not. Mayer encouraged them to focus on these incremental lessons, to treat each failure as a building block rather than a defeat. Outside, Allied bombers droned in the distance, a reminder that Germany's skies were no longer secure. Mayer often paused during tests to listen to the engines far overhead, imagining the P-38 seconds and B-29 seconds that might be flying in those same skies. The contrast between what Germany could dream and what America could execute was stark. The Reich's ambition to copy the B-29's pressurization system was more than a technical challenge, it was a confrontation with reality itself. By late January, Mayer had assembled a comprehensive report. 25 pages detailing every test, every failure mode, and every physical limitation they had encountered. It was honest and unflinching. The conclusion was clear. German engineers could not replicate the B-29's pressurization system under current material and industrial constraints. The project had reached a terminus not because of lack of skill, but because physics and metallurgy were uncompromising. Yet Mayer did not see it as failure. He wrote in the margins, in his precise, slanted handwriting, "Our understanding has advanced, even if replication is impossible. Every limitation mapped is a lesson for tomorrow's engineers. Physics is a teacher more ruthless than any commander, yet infinitely instructive." And so the Oberpfaffenhofen hangar remained alive with quiet activity, engineers recording data, building models, and simulating pressures they could not hope to contain. Outside, snow fell relentlessly, coating the mountains in a cold, indifferent white. Inside, the lesson of the B-29's pressurized cabin became a testament to the gap between ambition and reality. A gap defined not by courage or ingenuity, but by the immutable laws of science. Dr. Mayer, standing amid the scattered components and cracked models, finally allowed himself a moment of reflection. Dream of copying the Superfortress would never lift from German skies. But understanding it had transformed their approach, sharpened their insight, and proven that even in failure, knowledge endured. The horizon remained unreachable, but at least now, they knew precisely why. The first frost of February clung to the Rechlin Airfield like a frozen shroud. The Luftwaffe's testing hangars, normally humming with the mechanical symphony of engines and machinery, were subdued. Outside, the winter wind carved deep furrows into the snow-laden tarmac, and inside, engineers moved deliberately, each footstep echoing against steel and concrete. The B-29 pressurization project had entered its final, desperate phase. Dr. Rudolf Mayer walked slowly through the hangar, glancing at the rows of test rigs, fuselage sections, and experimental chambers. Though the initial euphoria of examining the American components had long faded, a certain grim satisfaction remained. The engineers now understood the precise limitations of German materials, alloys, and production techniques. Yet understanding alone could not overcome the gap between aspiration and reality. Dietrich approached, carrying the latest series of test results. "We've tried reinforcing the seams with magnesium alloys, layered steel, even some experimental duralumin composites," he reported. "No combination achieves the pressure threshold necessary for sustained flight at 30,000 feet. He paused. "The best we've done is 32,000 feet for 5 minutes, then the panels began to warp." Mayer exhaled slowly. He had expected this result, yet the disappointment was no less bitter. "And the valves?" he asked. Dietrich lowered his eyes. "The dual-redundant American system cannot be duplicated. Our valves either leak under sustained pressure or fracture under differential loads. We are at the limits of German metallurgy and machining precision." The problem was not ingenuity, it was physics, expressed through metallurgy and aerodynamics. The Americans had designed the B-29's pressurized cabin using advanced aluminum alloys that could sustain high altitudes, precision-engineered valves with minimal tolerances, and sophisticated stress distribution along the fuselage. Germany, by contrast, was facing material shortages, bombed factories, and rushed production schedules. The pressurization system was not a matter of design, skill alone, it required resources Germany could no longer supply. Despite the grim reality, Mayer refused to concede defeat entirely. He convened a small team of senior engineers in the main laboratory, their breath steaming in the cold air. On a large drafting table lay a detailed replica of the B-29 cabin cross-section, annotated with every rivet, valve, and seam. Mayer's finger traced the pressurization ducts, stopping at the relief valves. The Americans solved this, not through magic, he said. They understood the interaction between material limits and cabin pressure. Their genius is in distribution and redundancy, not just raw strength. We must learn from this, even if we cannot replicate it perfectly. The engineers nodded, some with grim determination, others with quiet resignation. They began a series of small experiments, simulating partial pressurization, testing scaled-down models, and observing failure modes under controlled stress. Each test, each rupture, each distorted seam was logged meticulously. Mayer believed that if the Reich could not copy the B-29, it could at least understand it, transforming an impossible dream into a repository of knowledge for future generations of engineers. Meanwhile, reports from the front filtered in. Allied bombers were increasing sorties over German industrial zones, and air raid alerts became routine. The Rechlin team worked under the constant threat of destruction, racing against both time and war. Materials were scarce, and yet Mayer pressed forward, convinced that the lessons gleaned from failure were as valuable as any victory. By mid-February, Mayer initiated an ambitious test. A full-scale mock-up of a pressurized cabin, constructed from the finest German aluminum and reinforced wherever possible. The objective was not to achieve American standards, but to push German engineering to its absolute limits. The test rig was enormous, filling the central hangar, with pressure gauges, valves, and strain indicators arrayed like a complex battlefield. As the team began pressurization, the gauges crept upward. Engineers held their breath, noting every creak, every shiver of the fuselage. At 20,000 feet equivalent, the cabin held. At 25,000, small seams began to bow, and rivets groaned under strain. Mayer watched closely, taking notes and calculating stress distribution in real time. At 28,000 feet, a panel buckled sharply, releasing a deafening hiss as air escaped. The cabin settled into a partial vacuum, and the test ended. It was a failure, but Mayer saw the subtle victories. They had learned exactly how far German alloys could stretch, which reinforcement techniques held the most promise, and how design tolerances affected performance under stress. It was knowledge that would endure long after the project itself had been abandoned. Later, as the engineers packed away the rig, Mayer lingered near a damaged fuselage section. The aluminum panels were warped, seals torn, and valves cracked, yet the segment remained a testament to both ingenuity and limitation. He ran his fingers along the surface, silently acknowledging the Americans' achievement. They had reached into the upper atmosphere, creating a flying fortress capable of sustained high-altitude operations, a feat Germany could admire, but not emulate. Outside, the snow continued to fall, muffling the distant roar of Allied bombers. Inside, Mayer drafted the final summary for the Luftwaffe's Technisches Amt, a detailed account of every experiment, failure, and lesson learned. His conclusion was unequivocal. The Reich could not replicate the B-29 pressurization system under current conditions. Yet the documentation would provide future engineers with invaluable insights into high-altitude design, material limitations, and stress distribution. In a letter to the Luftwaffe High Command, Mayer wrote, "We have reached the outer limits of our industrial and material capabilities. The B-29 pressurization system is beyond our physics. But the understanding we have gained is complete, precise, and may guide future aircraft design long after this war concludes. By the end of February, the project at Rechlin had shifted focus. Full-scale replication was abandoned, replaced with studies of high-altitude performance, partial pressurization, and lessons in stress management. The Reich's last dreams of a German B-29 had been grounded, but the engineers, scarred, exhausted, yet enlightened, continued to work, documenting the intersection of ambition, material science, and the immutable laws of physics. Dr. Mayer, standing in the center of the hangar, looked out the frost-covered windows. Beyond them lay a world in which his counterparts across the Atlantic had already flown into the thin blue sky, conquering altitudes and pressures that his team could only simulate. The Americans had not merely built an aircraft, they had mastered an environment Germany had only begun to understand. And yet, in understanding, there was solace. Knowledge, Mayer reflected, was the last frontier Germany could still claim. The bitter cold of early March still clung to the Thuringian hills. But inside Rechlin's wind tunnel laboratories, the atmosphere was tense, almost electric. Engineers moved in a careful choreography around the cavernous metal tunnels, pressure gauges, and control panels. The final phase of the B-29 pressurization study had begun, and it was more than an academic exercise. It was an acknowledgement of the limits Germany had reached and a desperate attempt to extract every last lesson from the American design. Dr. Rudolf Mayer entered the main control room, his eyes scanning the latest schematics taped to the walls. Every sheet represented countless hours of calculation, experimental testing, and bitter failure. The Americans had engineered the B-29's pressurization system with a mastery of high-altitude physics and materials science that Germany could admire but not yet replicate. But Mayer was determined to dissect it in its entirety. The project now focused on airflow and fuselage stress. The wind tunnel, a mammoth apparatus imported from the early 1932s and upgraded wherever possible, was capable of simulating the rarefied atmosphere at 30,000 feet. Sections of the B-29 fuselage recovered from the Yawata wreck and carefully transported via U-boat months earlier were mounted in the testing chamber. The engineers had installed an array of strain gauges, pressure sensors, and makeshift thermal controls to mimic the extreme cold at altitude. Mayer addressed the assembled team of engineers and technicians. Our objective is not to build an American superfortress. It is to understand why the system works and where our limitations prevent replication. The wind tunnel will show us how air interacts with pressurized surfaces and how structural integrity is maintained under dynamic stress. The first test began slowly. Air velocity increased incrementally, and pressure sensors recorded minute fluctuations along the fuselage. Engineers noted every vibration, every shudder. They watched how the panels flexed, how seams expanded, and how rivets responded under pressure differentials. Even at low simulated altitudes, the fuselage showed tendencies that German engineering had not fully anticipated. By mid-morning, the test reached the equivalent of 25,000 feet. The aluminum panels warped slightly, revealing weak points in reinforcement. Mayer adjusted the internal pressurization system, attempting to mimic the dual redundant valves used in the American design. Almost immediately, the strain gauges began to register anomalies, small tears in the metal, subtle but irreversible shifts in structural alignment. Note this behavior carefully, Mayer instructed. These failures are instructive. They tell us the limit of German alloys, the precision required in valve tolerances, and the impact of repeated pressure cycles. Every rupture, every shiver of the fuselage is a lesson we will record. The engineers worked methodically, cycling the pressure up and down, simulating ascent and descent. They observed how the cabin materials reacted not only to static pressure, but also to dynamic airflow effects that, in the B-29, had been carefully calculated to prevent catastrophic failure. The American engineers had understood the interplay between material elasticity, pressure, and temperature. In Rechlin, Mayer's team was learning the same lesson, but through trial, error, and meticulous observation rather than preemptive calculation. By early afternoon, the wind tunnel simulated 30,000 feet. At this altitude, the German fuselage sections began to fail catastrophically. Rivets popped, panels bent, and pressurized air hissed through fractures. Mayer remained calm, taking copious notes. "Record every anomaly," he said, "and correlate it with material composition, seam placement, and airflow direction. This is the only way we can translate these failures into usable data." Even as the experiments continued, the larger context of the war pressed down on them. Allied bombers were increasingly active over central Germany, and Rechlin itself was considered a likely target. Supplies were dwindling, aluminum and alloys were rationed, and the number of intact B-29 sections was finite. Mayer knew that every test, every stress simulation, had to be exact, measured, and irreplaceable. There was no margin for waste. In late afternoon, Mayer oversaw a final, more ambitious trial. Engineers mounted a fully pressurized cabin section, rigged with a sophisticated array of mechanical pumps and valves to replicate the B-29's altitude performance. The wind tunnel roared as air pressure simulated the thin atmosphere above 32,000 feet. The cabin flexed violently, rivets twisted, seams opened. And then, as the simulated altitude climbed toward 35,000 feet, the aluminum began to yield along an unexpected axis. Dietrich, standing beside Mayer, exhaled sharply. "The failure mode is not where we predicted," he admitted. "The American design compensates for thermal contraction and material fatigue in ways we cannot reproduce. Even if we had more advanced alloys, the complexity of their system exceeds our current capabilities." Mayer nodded solemnly. "Exactly. And this is why we document everything. These failures are not defeats, they are empirical truths. We now understand why the B-29 succeeds, and why the Reich cannot replicate it under existing conditions." The engineers spent the remainder of the day cataloguing every observation, photographing deformations, and recording data. By evening, the hangar was silent, save for the occasional creak of cooling metal. Mayer walked slowly past the battered fuselage sections, hands clasped behind his back. The B-29 parts, once symbols of American superiority and unattainable ambition, had become instruments of knowledge. He reflected on the journey from July 1944, when the wreckage first arrived, to now. The project had tested the boundaries of German physics, metallurgy, and engineering ingenuity. It had exposed not only technological limitations, but also the reality that some achievements, such as sustained high-altitude pressurization, were beyond the reach of wartime Germany. Mayer dictated the preliminary findings for the Technisches Amt. His report was precise, candid, and devoid of embellishment. The B-29 pressurization system represents a level of engineering that Germany cannot currently reproduce. Failures under simulated high-altitude conditions reveal limitations in material strength, valve precision, and structural design. However, detailed analysis provides valuable insights into stress distribution, airflow management, and pressure compensation strategies. These observations should inform future aircraft design and the development of pressurization systems. He concluded with a line that would resonate long after the war. "The Superfortress has shown us the limits of what is possible. Our duty as engineers is to learn, to document, and to ensure that knowledge endures, even if replication is impossible." Outside, the wind howled across the frozen airfield, carrying with it the distant echo of Allied bombers. Inside, Rechlin's engineers packed away the wind tunnel apparatus, the battered fuselage sections, and the carefully logged data. The Reich's final attempt to match the B-29's pressurized flight had ended not in triumph, but in clarity. They had reached the edge of possibility, and in doing so, had acquired lessons that would outlast the war itself. Dr. Mayer lingered by the hangar doors, gazing at the grey winter sky. Somewhere above, Allied bombers roared toward distant targets. Germany could not fly like the Americans. It could, however, now understand why, and that knowledge, Mayer believed, was the closest a Reich engineer could come to touching the skies the Superfortress had already conquered.